get started. Thank you for having us today. I'm Ikkou Okubo from University of Tokyo in Japan. Today, I'm going to talk about our research, the prediction of NFT bubbles using an extension of the log periodic power law model. Here's today's summary and an overview of the content. Our research responds to both societal and academic demands. Now, by extending the existing log periodic power law model, a kind of price prediction model, we successfully improved the prediction performance. Since some of you may not be familiar with the subject, I'll start my presentation by providing a quick introduction to NFTs. NFT is short for non-fungible token. It is based on blockchain technology, which guarantees the uniqueness and exclusive position of digital content. NFTs have been recognized as an asset and have been applied in a wide range of fields, including gaming and art. The NFT market experienced impressive growth in 2021. However, the market's expansion has also brought about some concerning issues, particularly bubbles that are causing risks to a variety of stakeholders, such as buyers, creators, and platformers. For buyers, the prices on NFTs are highly volatile, and there is a significant risk of suffering substantial losses in a short amount of time. Meanwhile, for NFT creators, the existence of bubbles may discourage them from striving to improve the quality of their NFTs. Instead, many creators are incentivized to produce low-quality NFTs for speculative purposes, which dominates their motivations. Moreover, platformers are also negatively impacted by price fluctuations. As an example, OpenSea, one of the largest NFT platforms, experienced a 99% decline in trading volume in just 4 months in 2022. Given these challenges, it is clear that there is a strong demand across the industry for bubble prediction. This study aims to respond to this demand and contribute to addressing the societal issue. Notably, there are currently no studies on predicting NFT bubbles that consider both endogenous and exogenous factors. In the stock market, researchers have explored the nature of bubbles, focusing on whether they are caused by internal or external factors. Endogenous bubbles refer to price changes resulting from mimetic investor behavior without external influences, while exogenous bubbles are caused by external shocks such as the COVID-19 pandemic. While a few studies have examined endogenous bubble in the context of NFTs, none have taken into account both endogeneity and exogeneity. This study aims to fill this academic gap and provide a novel approach to providing NFT bubbles. In this study, we have formulated 2 hypotheses. Firstly, we propose that by integrating external variables into an existing model that concentrates on endogenous bubbles, the model's predictive accuracy and explanatory power will be enhanced. Now, secondly, we hypothesized that extended model will further validate the result of bubble prediction. To achieve our research goals, we have adopted a 3-step approach, which I will outline on the next page. First, using the concept of drawdown, we select NFT projects for LPPLS analysis. Then we compare the performance of traditional one and extended LPPLS models. And finally, we calculate the bubble confidence indicator, which I explain later, to appraise the potential for near-term price decreases based on the price data from which external inferences are eliminated. We then compare the indicators of both models. First, in this study, we apply the drawdown concept when selecting the NFT project to be analyzed with LPPLS. A drawdown is necessary because the target data for the LPPLS analysis must be carefully selected to ensure that the time range does not include a single crash. Otherwise, the LPPLS model will not fit data properly. Drawdown and draw-up concepts were introduced to capture trends in price fluctuations. Drawdown is a percentage of change from one local maximum to the next local minimum price. Thus, as long as the price continues to fall, it is considered as a one single drawdown. A draw-up, in contrast, is a percentage change in price from one local minimum and to the next local maximum. A coarse grain drawdown in the middle part is used to capture downward price trends based on the bigger picture. Although a drawdown can be terminated by any small price increase, generally, price fluctuations contain a great deal of noise. Therefore, the original drawdown concept may not adequately capture downward price trends. So we introduce a threshold, epsilon, such that we ignore any regression smaller than this. Drawdowns that are large enough to be called crashes must be distinguished statistically from other relatively small or ordinary drawdowns. Previous research analyzed past markets and showed that nearly all drawdowns were well fitted based on the stretched exponential function. However, large drawdowns, on the other hand, called crashes, are said to deviate from this distribution. In this study, an outlier is a drawdown that deviates from the function of the 99.5 percentile of the distribution. Next, we explain the LPPLS model. First, we introduce the original model that focuses only on the endogeneity. The LPPLS model assumes rational expectations and irrational investors who behave in mimetic manners. And in this model, prices are explained only by time, not by other explanatory variables. Under certain conditions, it is said that the asset price follows the martingale process. In addition, by assuming that price falls by a fixed percentage kappa, the price dynamics can be as shown in the middle. By solving the differential equation, we finally get the last equation. And the function h called hazard rate is a susceptibility of the network system formed by investors. You might wonder how the susceptibility is determined, so I'll explain it on the next page. We assume that investors are forming a network influencing each other. Each investor has their own decision-making model where they make decisions considering both other decisions and external factors. Previous research introduced the so-called system sensitivity as a measure of the degree of sensitivity of a system to global influences from outside of the system. It expresses the probability of how likely a large group of agents is to be in the same state when an external influence is present. Since the network structure determines how the susceptibility behaves, the shape of the network is important. it is assumed that investors from the network called hierarchical diamond lattice. A notable feature of this network is that some agents are connected with more people compared to other agents. Then the susceptibility of the system chi is obtained like this. This chi can be seen as the hazard rate that I mentioned before. Now we can figure out what the hazard rate means. Please note that we assume the interest rate R and the stochastic discount factor phi is equal to 0. And we get the original LPPLS model finally. Next, I'd like to explain how we can extend the original one. To extend the original model so that external effects can be considered, we loosen the assumption. The LPPLS model inherently has a term that accounts for the risk. In the previous model, it is assumed that this effect was absent. Please remember that we assumed that those two factors are equal to 0. But this time we assume that the stochastic discount factor is a constant. Then we have to think about how to quantify the volatility factor sigma, this one. In this extension attempt, we will consider the impact of a term that includes volatility, which represents a risk. That is a term with a coefficient D in the left equation. We believe that one of the factors explaining the risk to the price of NFTs is the volatility of cryptocurrencies. This is because NFTs are not traded in common currency, but in cryptocurrencies, such as Ethereum. Prior studies have also indicated that NFT prices may be affected by cryptocurrency fluctuations. Therefore, we employed historical volatility as a risk indicator for cryptocurrencies, which means we used it as an external variables in this study. We use historical volatility for Bitcoin and Ethereum for 7, 30, and 90 days to compare each model. Next, in the third step, we calculate a bubble confidence indicator. This index shows how sure the endogenous bubble is happening. The larger the bubble confidence indicator gets, the more likely a bubble is happening. Let me explain how to calculate this. The bubble indicator is calculated by counting the number of times of an parameter satisfy certain conditions. The model is fitted for each time window from 120 days to 5 days. So there are 4 times fitting. The bubble confidence indicator assumes that if a bubble is endogenous, the parameter must satisfy certain conditions. And the conditions are obtained inductively from empirical evidence. Therefore, there are 2 drawbacks. First, even if no apparent endogenous bubble trend is detected, it may only be offset by exogenous influences, and hidden endogenous bubble may continue to grow. Second, apparent endogenous fluctuations may actually be a false endogenous detection caused by exogenous influences. To test for these errors, we calculate 2 kinds of bubble indicators. We first calculate the indicator for the original price data. We then calculate the indicators for the process price data from which external effects are eliminated using the fitting result. It can be justified that inherently the bubble indicator should be calculated for endogenous price changes. If both calculate higher values, then there is a strong possibility that an endogenous bubble is occurring. In this study, we use data from 4 major NFT projects: Decentraland, CryptPunks, Ethereum Name Service, and Artblocks. Although NFTs are inherently one of a kind and vary individually, even within the same project, this study focuses on the average price of the entire project. First, here are the results for the first stage of pre-processing. Crash was detected for only one project, Artblocks. So the rest of the analysis was done for the other 3 projects. Second, we compare the existing LPPLS model with the extended one for the 3 projects. The table below right shows the results for one project, Ethereum Name Service. The results indicate that the model is better when capturing external inferences. Each adjusted R squared in the extended model is higher than that of the original one, and IC gets smaller in the extended models, which means the explanatory power and forecasting accuracy increase when external variables are considered for all projects. Also, it can be implied that the asset may tend to be more sensitive to the cryptocurrency with which the NFTs are traded, in this case, Ethereum. And finally, we calculated a bubble indicator. The graph above is calculated on the original price data. Please note that this price variation includes both endogenous and exogenous. And the graph below shows the bubble indicator for the endogenous variation. In other words, the variation that is obtained by removing the external variation from the price changes. Comparing the two, some areas have high values in common, while others have high values only in one of them. With respect to the areas where the indicators show a common trend, we can say that this result enforces the claim of an endogenous bubble trend. On the other hand, if we look at the area circled in blue, the indicators calculated from existing data do not warn of a bubble. However, the graph below shows that this was only because the bubble tendency appeared to be weakened by exogenous influences. Taking into account the exogenous variation, this suggests that the bubble trend was in fact continuing, but external influences were making it behave in a way that made it appear otherwise. Lastly, let me explain the issues of this study. First of all, there is a room for improvement in the definition of a crash. In this study, we use the same definition of a crash as in existing studies on stock markets. However, the NFT market is more volatile than stock markets. Therefore, the criteria for a crash may differ from those in stock markets. Also, since only 4 projects were covered in this study, it was difficult to make cross-sectional comparisons that consider the characteristics of each NFT project, including factors like category or utility of an NFT project. And finally, there is a question regarding the parameter condition for calculating the bubble indicator. These conditions are empirically derived from stock market bubbles. Therefore, it may be possible to set different conditions for the NFT bubble definition. Thank you so much for your kind attention. If there are any questions about my presentation, I'll be happy to answer them. Or you can contact us later. Thank you so much.